So let's start. Today we are going to continue talking about domain adaptation problem. Let me quickly recap what we covered last time. So we are given a source domain. We represented it with distribution Q, X, Y. So we are observing M samples from the source domain. The samples comes in the form of xi sub s, xis, and yis. Again, for simplicity, okay, so let me actually be general. So we observe ms samples from source domain. These are labeled samples. From the target domain, these are labeled samples. From the target domain, we observe only unlabeled samples. The target distribution P, I observe, let's say, MT samples in the form of XIT samples. So the goal is to learn a function H from my hypothesis class that at the end of the day, what I care is the target error. So I look into the target error for this H, and that's the expectation on labeled target samples. Right? So in the test time, I'm going to have labeled target samples, and I want to evaluate how I perform in labeled target samples. So that's basically the goal in order to learn a function using labeled source samples, unlabeled target samples, in order to perform well in labeled target samples. Okay, I see there's a question. Please go ahead.
I just wanted to know whether this problem can be extended where the source samples are unlabeled.
Source samples are what?
Unlabeled.
Unlabeled. If source samples are unlabeled, then you know, it is not quite clear what kind of functions you can learn.
Like clustering or some clustering type of algorithms, can it work?
Yeah, sure. Yeah, so you can think about, you know, domain adaptation not for a supervised task, but for maybe an unsupervised task. Yeah, for sure. Yeah, but here our focus is basically a classification problem, and we want to learn a function in my source domain plus some unlabeled target domain in order to perform well in the target domain. Yeah, but you can think about some, you know, other variations. There are so many other variations of this problem. So I'm basically just going to focus on probably the most standard one, and hopefully, you know, you'll build some, you know, muscles and, you know, tools and techniques in order to be able to think about other related problems.
Yeah, thank you.
Sure. Okay, so last time we started talking about what are the assumptions that we have in order to be able to achieve goals of domain adaptation. One assumption was covariate shift, that we want the conditional distributions of Q and P to be the same. The other assumption was that the joint error should be small. If I had labeled target samples, then I want it to be successful. Otherwise, it's not going to be an easy problem. And the third assumption was that we need like a sort of a relationship between my source and target X's, the unlabeled source and target samples. And that's what we characterize using H divergence. So the H divergence is defined as between, let's say, QX. These are the marginal distributions of source and target. I look at the worst H that gives me the biggest difference between the probability of samples on one side of my classification boundary coming from the source versus samples that comes from the target and they fall into one side of my decision boundary. And again, we are considering a binary classification in all of these examples. And we looked into many examples to build intuition about this H divergence measure, which is really intuitive. So at the end of the last lecture, what we saw was that this quantity can be computed quite efficiently by training a classifier to classify source versus target unlabeled samples. In fact, there's a factor of 2 here. So in fact, half of this, H divergence is related to the classification loss, 2 times 1 minus the classification loss, if I'm training a classifier to classify source and target distributions. So that's basically the stuff we covered last time. Okay, so I'll start with the definition here, and then I'll state the main theorem that quantifies the target error based on quantities we have in the training time. Okay, so what is the definition here? So for a hypothesis class H, I'm going to define a symmetric difference hypothesis space. For the hypothesis class H, the symmetric difference hypothesis space, denoted by H delta H, is the set of disagreements between any two hypotheses in H. So in other words, I'm going to pick any two hypotheses, let's say HX and HX prime, H prime X, and I look into the disagreements between them. That's basically the XOR function. We are thinking about the binary classification, but all of these can be easily extended to the multi-label classification. So I'll talk about that later on. So this is defined, this defines a function. And if I look at for all pairs of H and X prime, H prime in my hypothesis, then the set of all H's that I'll get will define my symmetric difference hypothesis space represented by H delta H. So it will be the set of all G's, the XORs between H and X prime, such that H and H prime belongs to my hypothesis space H. All right, so this may sound a little bit complicated, but it is in fact really simple. Let me draw a picture just to show you how simple it is. Let's say I pick one function from my space H. So H of X is 1 on the right hand side. Let's say you pick another function H prime. Let's say it is 1 on that side of the classification boundary. All right, so I want to define a function G, which is their XOR. Let's look. So in this part, do they agree or disagree? H and H prime. I see agree. Why? H is 1. What about H prime? It disagree, right? So because H is 1, H prime would be 0. So in this part, they disagree. Same as here. So they disagree. So my G would be a function mapping the highlighted area to 1, other parts to 0. So if I just look at the place that G maps to 1, it will be the highlighted area in this picture. So quite simple. Okay, so I see some questions. in the chat box. Let me just monitor it for a second. Does that mean there is a separate test set for evaluation in the target domain? In the domain adaptation problem, in training, we don't have labeled target samples, but eventually we are going to deploy our method in the test time, and in the test time I am going to have labeled samples from target, but that's the evaluation time, so I cannot use that in order to train my model. Okay, so here is the main result. I think this is one of the probably like the most fundamental results in domain adaptation. This result has inspired many practical methods, and I'm going to, after this, talk about those methods. All right, so consider H as your hypothesis class. With a finite complexity. Let's say with a VC dimension to be D. VC dimension is the largest set of points that H can shatter. Okay, so we are given, let's say, unlabeled samples from the target, and we have labeled samples from the source. Again, for simplicity, assuming I have the same number of samples from source and target. Then with high probability, let's say with probability 1 minus delta, for any H in your hypothesis class, you pick any function, we have the following. Right? So at the end of the day, as I mentioned, we care about the test error. Right? So this is my test error. Not test error, target error. So I want to learn a hypothesis that performs well on the target, right? But unfortunately, I don't have labeled target samples. So this result shows that the target error can be bounded by error in the source. That's the source error. So that's good, right? So it means that if I minimize my source error, I'm basically minimizing an upper bound on my target error. So that is good. But we need additional terms, right? Because we know if source and target, they are not related to each other, then we are not going to be able to adapt a function from source to the target domain. So the additional term, in fact, comes from the H divergence. So if I look at the H delta H, so these are the disagreements between the two functions in my hypothesis class. And if I compute that divergence between unlabeled source and unlabeled target samples, that's going to be my second term. So we want this term, this divergence term, to be small. And remember, this was related to maybe a classification error that can distinguish between source and target samples. So if that classification error is large, then they are separate from each other. So then this divergence is going to be large. And although you can minimize your source error well, this term can be large, and then the bound can be loose. So it doesn't mean that if we have a small source error, that may not translate to a small target error. So because of this, this term is very important to be small. But if you remember, one of the examples I gave in the last lecture, it wasn't sufficient just to have a small divergence, because you could, like, you look at, different labelings, and these are looking at unlabeled source and target distributions. An additional term that we need here is to have a small joint error. If I had labeled target, I want my error to be small. and this is the joint source target error. So this very fundamental result tells me that my target error can be upper bounded by source error. That is good. A sort of a divergence between unlabeled source and target plus the joint error. If I had my labeled target samples and if I train a classifier, I should be able to do a good job. Okay, so I see there are some questions. Can you explain how to compute the middle term? The divergence term is not hard to compute, right? If you have a characterization of this symmetric hypothesis, which is not hard. Let's say you have two functions, you look at the disagreements between the two, then you basically train a classifier from this hypothesis class in order to classify your source and target distributions. You look at the proportions of samples from source that happens to be in these highlighted regions and look at the difference between the proportions of samples from the target in the highlighted region and look at the difference. But you want to find the worst case classification that can separate your source and target distributions. In practice, there are some approximations done in order to use a sort of divergence in the training itself. Right, so I'm going to talk about those practical algorithms next. Any other questions?
I have another quick question about the symmetric set difference. So the one thing that puzzles me is that we have it for any two functions from our hypothesis class.
Yes.
And I'm curious as to why this doesn't ultimately become like trivially the whole space if we just take one function h and then its negation. Don't they always disagree? Or I'm sorry, it's the x is such that no two functions agree? Is that what we're saying?
So you pick two functions, you pick two functions, and then you look at the disagreements between them. So let's go with your example. Let's say my hypothesis class is symmetric itself, right? So if I have a function, I have, let's say, the complement of that function. Right, so you pick that function, you pick the complement of that function, and then yes, for that you will get the entire space. And
I see. Okay, so then
in the entire space, then the fraction of let's say target and source samples, they're roughly the same, right? It's basically exactly the same.
Right.
That will give you a 0 in your objective. But you want to find some functions that give you the highest discrimination between source and target.
I see. Okay.
Basically, you want to highlight parts of this space that they are in fact different. That the ratios of source and target are different, and that part of the space should be highlighted by the disagreements between two hypothesis functions. Make sense? Good. Okay. All right, so this very fundamental result inspired many practical algorithms. So next I'm going to switch gears and talk a little bit about more practical domain adaptation methods. Practical domain adaptation methods. Okay, so you can think about domain adaptation is not a new problem, right? So it's a very important problem. So even before the deep learning era, people, they have thought about this problem, and there have been really interesting ideas to deal with this problem. So prominent works, I would call them classical methods. These are like domain adaptation methods. By classical, I mean pre-deep learning. There are many interesting methods proposed based on either metric learning. Metric learning, basically what it does, it learns a embedding metric like a W matrix that tries to somehow align your source and target, and it learns the matrix W in a either symmetric or asymmetric fashion. Other areas of work look into subspace alignment. Again, if you, for example, look at the PCA subspaces of your source and target, they can be very different. So the whole idea of subspace alignment is to find a transformation to align these source and target subspaces. There are some classical results based on MMD based distribution matching. So I'm going to talk about the deep learning version of these methods later on. There are methods based on sample reweighting, and selection. People thought that maybe if we upweight or downweight samples in source or target, we can try to make the two distributions closer to each other, and many other classical methods. So these are most of them pre-deep learning, and they're mostly based on some linear algebra solutions, closed form solutions, trying to map either distributions or some subspaces of source and target distributions into a common space. Okay, so here we are going to, in this lecture, we are going to focus on modern methods. So by modern methods, I mean methods based on deep learning, deep domain adaptation methods. Okay, so let's start with perhaps one of the first such methods proposed by Gannon and co-authors. All right, so if you think about this upper bound that we have, so yes, we have the source error that we want to minimize. That's the first part. But we also have a sort of a divergence between my source and target, and I hope to learn some sort of embeddings of these source and target distributions such that a divergence, H divergence between them is small. Right? So we also have seen some result that relates the H divergence to maybe a classification error between source and target in order to classify source and target samples to see if we can distinguish between the two. Okay, so here's the basically framework that this paper considers. We have X, which is my input. It goes to an embedding function. So this is called F, or it's an embedding function. It's a deep network. Let's say you have multiple layers. So it basically, at the end of the day, provides some features. And we use these features in a classification, right? So I'm going to have a classification. Let's say C1, this is my classification. network in order to map these features ultimately to labels, right? So these are my labels that I wanna predict at the end of the day. Okay, so if I just use my source, labeled source samples, I can train F and C1. So how I would train that, I'm going to minimize the average error on my labeled source samples. I'm going to look at my labeled source samples, XY, from distribution Q, and that would be a classification loss C1 composed with F, and this is my label. So that's basically the first term in this upper bound that we had before. Right? So that's what I'm going to minimize. But now the thing is the following, right? So now if you, instead of your source X, if you use the target X, then you are going to have some other feature distributions after the embedding, right? And we want to basically make sure that they are not different from each other, so they are aligned to each other. So in order to deal with that, I'm going to train another classification, another classifier in order to classify source and target. Okay, so we basically train another classifier, let's say C2, but this classifier is not interested in like classifying the labels, right? So the goal is to classify samples by looking at their features to see if they come from either source domain or the target domain. So this is the domain classifier. So if this domain classifier is successful, then I'm not basically aligning my source and target features well on top of each other, right? But if this domain classifier is not successful, it means that basically the embedded features of source and target, they're roughly speaking on top of each other, that my classifier is not able to classify between the two. So what they have proposed is to maximize the domain classification loss. So we are going to use lambda times, let's say, loss of domain classification. Right, so basically C2 tries to maximize the domain classification. So this is acting like an adversarial classifier to see if it can distinguish between your source versus your target samples by just looking at the feature embeddings. That's why we have a negative here. So it maximizes that error. But my F and so let me undo it. My F embeddings and my C1 tries to minimize this classification error. And that's how we are going to train. And hopefully, if we converge to a good solution, the error here is not going to, be large, meaning that is going to be large, meaning that my classifier, my domain classifier, is not able to classify between source and target. And then that kind of, in a hand-wavy fashion means that they are aligned to each other. Therefore, if I use my target samples here, then hopefully that will lead to a good target error as well. All right, so that's basically the idea of this paper. Let me pause and take questions. Also, apologize for some of the noise. I don't know if you guys hear it. It's neighbor doing reconstruction or construction. Hopefully that's not like too loud. All right, so there's a question, is this optimized in a min-max fashion? No. So there's a single minimization, right? So you have minimization on FC1 and then over C2, but there's a negative here. So it is not min-max. You can think about a min-max formulation. I'm going to talk about that, right after this. Okay, good. Okay, so there's a question, is that like the H divergence? It is kind of like the H divergence, right? Because it basically, 1 minus the classification loss was basically twice my H divergence. And if the function f composed with C2 is rich enough to quantify the symmetric differences between my hypothesis functions, and if I could solve this maximization of the classification error exactly, that would be exactly my H divergence. But there are some approximations and hand-wavy assumptions along the way. Okay. In general, what we want to find this mapping, this embedding, such that the embedded source and target distributions, they are on top of each other. So we have f of source distribution, f applied to the target distribution to be close to each other in the distribution. So that's basically the goal of many of these practical methods. So in general, we want to find a mapping. Sometimes it is referred to as embedding f, such that if I apply f on qx, which is the unlabeled source samples, in distribution it is close to f applied to p of x, which is the unlabeled target samples. Source, and this is the target. Right? So that's the goal of many of practical domain adaptation methods. Okay, so let's revisit the framework that we looked into. So here I apply f to x, I get some embeddings, then I have a classifier, let's say C1. So here, this is my embedding function. This is the classification. It's the label classification. Now what I'm gonna do, I'm going to look at this part, right? This is the f of qx or f of px. And I want the distributions of source and target after applying the embedding function to be close to each other. Okay, so what we are going to do here is to penalize the distance between fqx and fpx. Right? So that's basically the idea of having a small distance in the embedding space. Okay, so let's see what kind of distances we can use and what kind of distances people have used. All right, so example 1. So you can use a Wasserstein distance, right, between source and target. I'll talk about that. But you can use some other distances as well. Let's start with a distance that classical domain adaptation methods in fact use, and that was Mmd distance. Mmd distance is the basically maximum mean discrepancy distance. Discrepancy. All right, so let me define this distance because it is useful not only in domain adaptation but in many other problems. For example, in GANs and other problems, Mmd distance is a popular distance measure. So let's define f of x for simplicity, xi tilde. Just to not carry the notations f here. So these are the embeddings for different samples we have. All right, so the MMMD distance between the embedded source and target distributions is defined as the following. So I have embedded Q distributions. I have embedded target distributions. For simplicity, let's assume we have the same number of samples between them. So it is a very simple distance. So I'm gonna pick a function phi, whatever function that you like. And I'm going to apply that function on my source samples. And I'll look into the average of values that I get over my source samples. And I would apply the same function on my target samples. And I would look into the average values that I would get by this application. This phi function potentially maps, let's say if my samples in D dimension, let's say here x tilde is in R dimension, this function potentially maps these R dimensional samples to a very, very large space. It can be like polynomials of degree 10 or any other functions. So that's basically the definition of the MMMD distance, right? So you pick a function, this function is fixed, we are not optimizing over this function. And then you apply this function on the source samples and target samples and look at the mean difference between the two. And that's the MMMD distance. But one issue here is that this D, capital D, can be very, very large, right? If you're looking at, like, you say, polynomials of degree k, then you are really expanding your features to a very, very large space. So how can we compute this efficiently without requiring to explicitly compute phi of x's? You have already seen this, so you should be able to answer it.
Kernel trick.
Kernel trick, yes, right? So it is basically very similar to the kernel setup. So if I had a squared here, right, I could open up this summation, then I would get the inner products between the phi's, and that inner product basically is the kernel function. Right, so basically the idea here is to use the kernel trick to compute MMMD distance without explicitly computing phi's. All right, so how can we do that? If I look at the square of my MMMD distance, if I look at the square, because I don't have a square here, so if I look at this, then I can just open up the norm square. right? Then I'll have like phi xi s's inner product with each other. That will give me one kernel term. I'll have phi xi t's inner product to each other. I'll have other kernel term, and then I'll have the cross inner product between the two. So what I'm gonna get is something like this, 1 over m squared. So I'll take this out. Sum over I and j. So I'll get the kernel values between my sources. And I'll get the kernel values between my targets. Minus 2 times the kernel value between the source and the target. Right, and that's gonna be the MMD distance. So therefore, an MMD based domain adaptation optimization can be formulated as the following. And I think this is done in this following paper. Where we are basically picking model parameters, minimizing the classification loss. What's the classification loss? I have C1 applied to my embeddings on the source sample, plus I want to penalize the distance between my unlabeled source and target, and I'm going to use the MMD distance in order to do that. So that will be the distance between unlabeled source and unlabeled target after applying this embedding function. And we solve this optimization problem. Okay, so let me pause and see if there are any questions. There's a question, those are all X tildes, right? Yes, yes, you're right. Yeah, because I'm defining my distance in the embedding space. Any other questions? Can we use Wasserstein in domain adaptation optimization? There's a question, so let me first answer that. Why is it required to project X tilde to higher dimension? So that's how MMMD is defined. There is no requirement to define. So MMMD is defined using basically in a Hilbert space when you are mapping your X's or X tildes to a higher dimensional spaces like kernels, and then using basically defining your similarities in the higher dimensional space. That's just the definition of the MMD distance. But the basically question is that do we need to do that, right? So are there some other distance measures that we can use without needing to use the kernel functions, because these functions are fixed, right? So it may not be able to represent proper distance measures between the distributions that we have. So can we use, for example, Wasserstein distance? Can we? So basically, instead of this MMMD, can I replace it with Wasserstein? Come on, guys. So the question is it possible to not use MMMD and to use Wasserstein instead of that? And what would be difficulties in that case? Okay, no answer. You guys need to review the Washenstein lecture that we covered in the Gan lecture, right? A little bit disappointing, but fine. Yeah, we can use it, but we'll have some additional computational difficulties, right? So here we have the classification loss. But if I replace it with, let's say, a Washenstein loss between my source and target, the Washenstein distance itself is computed via another optimization. Right? So using the control-rich duality, we know this Washenstein can be written as max over a discriminator function, which is one Lipschitz. The expected value of the f applied to the source minus expected value of my discriminator function applied to the embeddings of my target. So here I'll get a min-max type optimization, and the way that I can solve it is using alternating gradient descent ascent. So one difficulty here is how to quantify, how to characterize Lipschitz functions. Right, so there are some approximations here, similar to the GAN, that we use neural networks to characterize the discriminator. So instead of exactly optimizing the Washenstein, so oftentimes we optimize over D, which is a neural net, maybe with some regularizations on weights or some spectral regularizations, that quantity that we have here, right? So the same quantity here. So this is also called IPM distance, or integral probability metrics. And that's what people do in practice in order to approximately use Washenstein in this setting. Okay. Now we are in this business of using different distance measures in order to penalize the source and target embeddings. You can use improved versions of these distances in order to have a better alignment between your source and target distributions. Use improved and perhaps robust versions of Washenstein in domain adaptation. Right, so I talked about in the GAN lecture, I talked about our recent work introducing robust Washenstein, which is a variation of a Washenstein distance that is robust against some outlier samples or some samples that are noisy. And that can be very important in domain adaptation, because maybe when you are aligning your source and target distributions, maybe you can align maybe 95% of your samples, but there may be 5% that are very hard to align. And those may, in fact, mess up your embedding function. So you want to somehow ignore a small percentage of samples that are very hard to align to each other. So that's why using robust Washenstein can be very helpful in domain adaptation. And that's basically the work that Yogesh, Rama, and myself proposed in this year's NORPS. And especially for some other, for mixture models, you may have like different ratios of mixtures in your source and target in order to have a balanced mappings between source and target. So we introduce also in another paper a measure called normalized Wasserstein by the same authors, I think ICCV, that looks into aligning the proportions of mixture models in order to have a better embeddings. So using them improves the quality of domain adaptation in general when you have noisy samples or where you have mixture models. Okay, so there's a question, how do we solve the total optimization alternating gradient? Yeah, so you get like a min-max optimization here, and then you solve using maybe simultaneous or alternating gradient descent ascent. Okay, any questions? All right, so let me tell you one more approach based on image-to-image translation. So this is another practical approach. Which is based on methods developed for image-to-image translation. Specifically, we are going to focus on a method called cycle GAN. Which is a very popular method to have a translation between unpaired images. Introduced, I believe, in 2017. Okay, so what is the idea here? So you have a source where you have some labeled samples, and you have a target where you have only unlabeled samples. Right, so the idea of image-to-image translation in an unpaired fashion is that, let's say, if you give me some images in a particular style, and I want to change the style of those images, and I have some other images from another domain, another style, but I don't have a paired version of them. So how we can transfer the style from one domain to another domain. So that's basically the key idea of these unpaired image-to-image translators. And CycleGAN is one of the very popular and very successful such methods. All right, so these types of domain adapters, they use basically same ideas. So here we are going to train two functions, one function mapping from source to target. If you give me a source sample, I'm going to just apply this function and get a sample that looks like the sample comes from a target domain. So that function is called source to target. And we'll basically train another function that maps a target sample to the source domain. And that's what we call target to source. Right, so these are the two functions that we have. Okay, so yeah, we'll have the first term will be the same old, minimizing the classification loss. But what about the other term? So we want to learn these functions that are somehow providing some consistent samples from the other domain when we are mapping with these functions. So for that, we need to have basically two discriminator functions, discriminating samples that are being mapped from source to target, from actual target samples, and the other function that will be discriminating samples of target samples mapped to the source domain and actual source samples. All right, so the first loss, that's called Gan loss, it inputs the actual source samples, the target samples, these are unlabeled. The function mapping source to target and a discriminator. So this D is a discriminator in the target space. That's why it is labeled with T. So the Gan loss is basically similar to training a classifier or a discriminator D that tries to distinguish between actual target samples and the samples coming from source to the target domain using this function. So the loss would be, let's say if you have a actual target sample, I'll maximize this probability. And for source samples, I'll look into the log of 1 minus the probability computed by this discriminating function. But for the source, I'm going to apply that function, right? So the function that maps my source to the target. Okay. So here D tries to, this is basically the logistic loss, classification loss, using the D as the classifier or the discriminator. And I'll maximize this over D, trying to find a discriminator that can actually discriminate between the actual target and the source samples transferred to the target domain. So the second term, you can imagine would be very similar, defined on source target, but then here I'm going to look at the function mapping target samples to the source domain, and I'm going to have a discriminator in the source domain to discriminate between the two. All right, but one of the key ideas of the cycle GAN is to introduce one additional regularization loss. It's called cycle consistency loss. So the idea is that if I have a sample, let's say from the source, then I use this function source to the target, I get to this point in my target domain. And then if I apply the function mapping the target to the source domain, the point that I'm gonna get here would be what? GT to S applied to GS to T applied to the source sample. I want these 2 points to be close to each other, right? So I want them to be roughly speaking the same. And that's the cycle consistency term that is being added to the loss function. So here we have cycle consistency term between source, target, and the two functions that maps from one domain to another domain, defined as I'm going to look at all of my source samples. Then I'm going to look at L1 loss between basically the error. If I go to the target domain, come back, what is the error that I'm going to observe? Source to target, apply to the source samples, and I'll have basically the same term. If I start with the target sample, go to the source, come back, and I'll have another such a term. So the only difference here is that here we are going to have a reverse ordering of the source to target and functions. Okay, so the ultimate objective function would be, okay, so I have a classification loss as before on the labeled source samples, and I'll have the cycle Gan loss, which is basically the sum of the three terms that I have here. So one term is this function, the other term is this function, and the third term is this function. So I'm going to minimize this over my parameters theta, but I'm going to maximize it over the discriminators, the source and target discriminators. And that's basically the main idea of domain adapters based on image-to-image translation. So I thought to mention this because cycle GAN is by itself is an important method to transfer styles or some other properties from one domain to another domain, and that the whole idea is basically adding this cycle consistency term. So it is not very difficult. I see there's a question. Amir, go ahead.
What if instead of the cycle loss, there was some sort of a normalizing flow type generator in which it was by definition invertible or by design invertible? Do you think that's feasible? Or?
Oh, so you want to use an invertible function going back and forth between the two domains? Yeah, I think that's doable. So not sure if people they have looked into that, but that's doable. So I'm not sure if it is going to give like a very high quality translation. So that's something to be seen, because sometimes these bijective functions are not very powerful. Obviously, we can concatenate them to increase their expressiveness, but sometimes they may not be able to be as good as some other non-bijective neural networks.
Thank you.
But that's a good idea. Yep. All right, so let me see how much time I have. So I have about 10 minutes. There's a question. Can't we use a pre-trained cycle GAN on the source and target instead of training it with the classification? I'm sure you can, but probably this version works better. That's why they have done it in that fork. But you can think about some other related ideas, right? So the whole purpose here is that I provide some angles that people they have looked into, and then you can maybe further investigate each of them and see whether or not it can be improved. Make sense? Okay. There are some other tricks people use to improve the performance of domain adapters. These tricks sometimes use domain-specific batch normalizations. It usually helps. There are some entropy regularizations that people they use in order to basically try to push source and target distributions closer to each other. So I'm not going to go into these tricks. As I mentioned, one is domain-specific batch normalization. There are some interesting entropy-based regularizations that usually helps in practice, but probably I won't be able to cover that. So if you are working in this domain, you should take a look into these practical tricks. All right, so let me go back to the assumptions that we started with, right? So the assumptions that we started with to argue that domain adaptation can be successful, we have three assumptions. The first assumption was the covariate shift assumption that says the conditional distributions between source and target should be the same. the second assumption was that the divergence between my source and target distribution should be small. And the third assumption was that if I had labeled target samples and if I include that in my training, this should also be small. So these are the three, roughly speaking, practical assumptions we have in hand. So one question that I think some of you ask, and folks have asked in the literature, is that are these assumptions necessary? Are these assumptions necessary or sufficient, right? So which of these assumptions are sufficient in order to argue that the domain adaptation is going to be successful? And this question is being studied by another paper by Ben David and co-authors, titled The Impossibility of Domain Adaptation. So the gist of the result of this paper is that the first assumption that, in fact, a lot of domain adaptation methods, they are arguing that's the most important assumption. This assumption is actually not really strong. So you may be in a situation that covariate shift assumption is holding, but the domain adaptation is not going to be successful. But the second and third assumptions, they are in fact necessary. So without these two assumptions, we won't be able to have a successful domain adaptation. Okay, so I have a few results from this paper, but I have only 5 minutes. Okay, so let me. Okay, so unfortunately, I don't have time to go into the details of examples of this paper, really interesting examples. You should take a look, but let me just, have the gist of the results. Basically, through some interesting examples, they show that covariate shift assumption is not sufficient. You can come up with an example where covariate shift holds. The divergence is in fact is small, but the joint error is large, and therefore you won't be able to have a successful domain adaptation. In fact, the first example, one of the first examples I gave in the previous lecture, where we had like the labels flipped, it can basically show that it is very important to have a small joint training error. So the example in this paper is very close to that example that I mentioned. And they have two interesting theorems. One is about the necessity of small h divergence assumption for domain adaptation. They argue that if covariate shift holds, if you have a small joint error, basically if assumption 1 and 3 holds, still you can find pairs of source and target distributions such that there is a labeling function that will provide you assumption 1 and 3, but violating assumption 2, and then the test error would be very large. With high probability, it would be larger than half. So therefore, second assumption is necessary to have a successful domain adaptation. And similarly, they have a result on the necessity of having a small joint training error between source and target if we had labeled target samples. Okay, so In the last minute, I just want to say, in the last 2 lectures, we talked about unsupervised domain adaptation. Where we have labeled source samples plus only unlabeled target samples. So another interesting area is the semi-supervised domain adaptation, where you have, okay, labeled source samples, unlabeled target samples, but you have a few labeled target samples. These labeled samples are not sufficient to just train a classifier using these samples. Maybe you have 1 labeled sample per class or 5 labeled samples per class, but it's interesting to see how we can use these few labeled samples in order to further improve the performance of domain adaptation methods. And there are some interesting results in this domain as well.